The derivative of constant functions sure is nice to work with. It's relatively straightforward, but of course we're not only going to be working with constant functions. We want to be able to work with all sorts of different functions of x. So we're going to jump to the next most complicated case, which is power functions. So I'm going to look at these different powers of x and see how the derivative unfolds, and then we'll see if we can generalize that process, see if we can come up with a method to find the derivative for any power of x. So the derivative of f of x equals x, if I wanted to take that derivative using the four-step process, I'd find that the derivative of this function is f prime of x equals 1. If I wanted to make my function a little bit more complicated, now I'm going to work with f of x equals x squared. We'll add 1 to the power. If I wanted to take the derivative of x squared, I could do that using the four-step process. I'd find that f prime of x is equal to 2x. If I wanted to add 1 to the power, now we're going to work with f of x equals x to the third. If I wanted to take the derivative using the four-step process, I'd find that f prime of x is equal to 3x squared. Let's do one more just to be sure. If I add 1 more to the power, I work with f of x equals x to the fourth. I could do that four-step process. Here it starts to get pretty darn lengthy, but the derivative of x to the fourth you would find is 4x raised to the third power. I'll link the process of finding the derivative using the four-step process for some of these functions. I'll do the first 3 because after that it starts to get pretty long. But I want you to take a look at these functions and see if you can take a guess at how we can get from our function, let's say how we get from f of x equals x to the third to f prime of x equals 3x squared. What are we doing to this function each and every time? I want you to pause the video, think about it, maybe jot down your answer, make a guess, and then we'll come back and talk about the power rule. So at this point, you've made your guess, I'm sure. The two things that we're doing, and really we're following a two-step process every time. What are we doing with this power? If I look at, say, f of x equals x to the third, I think this is where the pattern starts to become a little bit more apparent. Well, we take this power and we move it to the front, and we don't want to just say move it to the front. We want to use a math word, so we are multiplying over here by our power. So our first step in each one of these is to multiply by the power. So we're going to start each one of these by multiplying by the power. And then after that, what happens? Well, I started here with the power of 3, and then it became 2. In this example, I started with a power of 4, and I went down to 3. I can even go backwards. Here I started with a power of 2. Even though there's not one written, I went down to a 1. So I'm going to start by multiplying by the power, and then my second step, I am going to subtract 1 from the power. And if you can follow these two steps, this is what the power rule tells you. It tells you how to take the derivative of a power function. So if you're working with f of x equals x to the nth power, then your first step is to multiply by your power. So I'm going to multiply by my power of n. And let's talk about the derivative. F prime of x equals, I'll multiply by my power, n times x. What do I do next? I subtract 1 from the power. So my power is no longer just n. I need to subtract 1 from this power. So this is how it looks in its general form. You don't necessarily need to memorize it. If you're more comfortable with this two-step process, then you can by all means rely on that two-step process. But this tells us how to take the derivative of any power function, whether our power is positive or negative or a whole number or a decimal or a fraction or a big number or a small number. It works for all of these. So it's a really, really handy tool. It makes finding the derivative a much, much quicker process. One thing I want to address before we jump into some examples is this first derivative that we found up here. It might look a little bit different. Here it says, well, the derivative of f of x equals x is 1. Why is that the case? Well, the power on that x, if we're working with f of x equals x, even though there's not 1 written, the power there is really 1. So we're really working with f of x equals x to the first power. And if I wanted to verify that the power rule works in this case, we'd say, okay, I'm going to start by multiplying by the power. So f prime of x is equal to 1 times x. And then I need to subtract 1 from the power. So I'm going to have 1 minus 1. So this really is 1x raised to the 0 power. But we know that any number raised to the 0 power, that's going to be 1. So 1 times 1, that gives me 1. So hey, there is my derivative. It does, in fact, match up with the power rule. So that's pretty handy. So let's jump in and let's find some examples using our power rule now. So if I'm working with f of x equals x to the 5th and I want to find f prime of x, well, f prime of x, this is just a power function, so I'm going to start by multiplying by my power, which is 5, and then subtract 1 from my power, 5x to the 4th power. And there's my derivative. If I wanted to work with a bigger function, here I might want to find dy over dx. Remember, that's just another way that we can write the derivative. If I was working with y equals x to the 100th power, this is still just a derivative. I can still use my power rule, multiply by my power of 100, x, and subtract 1 from my power. I now have to the 99th power. So there is my derivative. So I've got 99 problems, but this problem ain't. I'm sorry, I could not resist. I had to make that joke. G prime of x equals g of x equals x to the negative 2. So if I'm working with this function right here, the power rule does work for negative exponents, but we do just need to be a little bit careful with our power. When I find g prime of x, I'm going to, again, multiply by my power, so negative 2x, and I want to subtract 1 from this power, and here we just want to be really careful with our signs. I really want negative 2 minus 1. I don't like subtraction. I always like to think of it as plus a negative 1, negative 2 plus negative 1. My new power should be negative 3. And there is my derivative. So if you're working with negative exponents, please just be very careful with your signs. Part D, this last example, this one looks a little bit different. I want to talk about this notation before I jump into actually finding the derivative. This piece right here, this d over dx, this is really like a, if you think about it in like English, it's almost like a verb. It's telling you, it's saying, hey, take the derivative with respect to x of this function. So it's actually kind of like a set of directions. It's saying, take the derivative of this function. So I still just am finding a derivative. Even though my power is a fraction, I can still use my power rule. We'll just have to be a little bit careful here. So if I want to take the derivative, I'm going to multiply by my power, so 3/2 times x, and then subtract 1 from my power. If you need to, we can do that scratch work off to the side. I really want 3/2 minus 1, but that's 1 over 1. In order to subtract, I need a common denominator, so we'll multiply by 2 over 2. 3 over 2 minus 2 over 2 would give me a new power of 1 over 2. So that would be my new power here, 3/2 x to the 1 over 2 power, and there is my derivative. So these are really pretty nice cases because for any power function we work with, we can use these two steps of multiply by the power and then subtract 1 from the power. Now, in some cases, we are going to have to do a little bit of clever rewriting in order to utilize the power rule, and I'll show that in our next video.